Hello. So now it's already time, so I will start it. So remember, last time I introduced so many groups. Basically, they are from the matrix group, and then we have written down two basic exact sequences, or maybe three. So let me just recall what were those sequences, and we use them to compute the orders. All right, in a finite case. So the one was, and so GLN or GLKV, and V is the finite dimensional vector space. V finite dimensional vector space. So if I don't say, always V will be finite dimensional vector space. K vector space. K is the arbitrary field. And more interesting cases will come from K is finite field. So GLKV to K cross. This is the determinant map. This is surjective. And the kernel is precisely the spatial linear group, SLKV. And note the notation I am putting one here because these groups are multiplicative groups. If they were additive groups, I will put 0. So that is standard. So another one which relates PGL, PGLV. So that anyway, I will also do it more today because I will explain what that kind of a group is, and already you have exposure to this group in some sense. That also I will record. So GL KV to then PGL KV to 1, and then there is a center here, but center we have identified with K cross. Remember, this is the center of GLK. That is what we have identified. They are precisely the scalar matrices. So the diagonal entries are equal, that is A, and A is in the non-zero element in a field. So that is precisely the center. So this is another one. All right, and therefore from here we get an expression that from here you get another exact sequence, PGLKV, that is going into K cross, and then I use this notation, N on the left upper suffix of upper subscript of this K. I will explain that, and the kernel is precisely the PSL. And this is called projective linear, this is called spatial projective linear. And now what is this? This notation? That is very easy, but I will write them in the form of exercises. Probably you have seen these. If you are not, treat them as your basic requirement and do them. They are very, very easy. So let me list so that you will have at least something to do at easy level. So I have collected them on my sheet here. So hold on this for a moment because I will write them for general group. So let G be an abelian group. Abelian group. Because I am going to use it for K cross. And K cross is abelian because K is a field, multiplication is commutative. All right, and it is very important to consider these maps. They are called power maps. Power maps. So that is a map from G to G, X going to X power N. This is obviously a group homomorphism. That is where I use the fact that it is abelian. And whenever you have a group homomorphism, you have two subgroups attached to that, the image and the kernel. So the image of this group, so image, I am going to denote by NG. Obviously, I don't want to put this on the other side because then one will confuse with G power N, which is G cross N times. So that is what I have no choice but to write it on the left side. And therefore, don't claim that you don't understand this notation. So this is why, what is that image? Image is all those powers, X power N, where X is varying in G. And what is the kernel? Kernel will be equal to, again I am writing it, where can I write N in the notation? I have no option, I have to write it here, because all other places are occupied. So therefore this is all those X in G such that X power N is identical. E. So these are the subgroups. When is it injective? When the kernel is 0, that means there is no nth root for X power N minus 1. Think of 1 as an identity element, and therefore think of this kernel as the solutions of the polynomial equation X power N minus 1 in G. Solutions of this in G. That is what it is. So in the field case, we are well off because we study the polynomials over a field very extensively, and that is very ancient study. Still it is very active. Still it is not very well understood. So we need to study. Okay. So injectivity we can describe. Surjectivity also we can describe, that is every element is a power, nth power of somebody. Then it is surjective. Okay. So when is this map automorphisms? When is this map automorphism? When is the power map? When is the power map? Automorphism. And obvious answer. That means it is surjective. So I will write the answer. That is if and only if N should be co-prime to order. N is co-prime to the order of G. Now that means GCD of N and order of G is 1. And you see here, that is why in the last lecture, just now what Tithi asked us, why is this? The order is Q minus 1 and N is that power, and therefore this is the condition. All right, so you should do these exercises. These are small exercises, you should do it. All right, now one may ask again, next question. These are simple questions, but interesting, and also they are applied somewhere in our discussion. All right, so how many automorphisms are there? And by the way, this last comment, I don't need, I only need that finite. This is for the finite. So this is I am asking when G is finite. If G is not finite, the GCD doesn't make sense. All right. So how many such power maps are there? So how many? So G finite again. Then only you can ask such question. G finite. Then how many power maps are automorphisms? Answer is again very simple. Answer, it is phi of order G, where phi is Euler's quotient function. Actually, the earlier observation gives you the answer to that also. All right, so you should do these easy exercises. You may still have difficulties. You can raise the difficulties in tutorial sessions. All right, now why did I listed them so carefully? For the following reason. I want now you to calculate for various k. So k, suppose k is f2. K is f3. K is f3 and k is f4. Now here f4 doesn't mean it is Z mod 4. It is a field with 4 elements and we know it exists because 4 is the power of prime number 2. So in all these cases, you should note down what are the cardinalities of GL. Of course, you found it out. GL and F2, you know. Similarly, SL and F2. Similarly, PGL and F2. And similarly, PSL and F2. And you will be surprised in all these cases, in F2 case, all their cardinalities are equal. So this is, I am asking, merely check this. Check this. And you have the formula. You have the formula for this, and therefore for this, for everybody, because these three exact sequences will allow you to compute. Now similarly do it for F3 and similarly do it for F4. These are small examples and you know these fields and therefore you should do this. So this is an algebraic description. But now I want to also come as a geometric discussion, geometric descriptions of these groups, and all you have some exposure, I know, from complex analysis, for example, or even from topology. So the first thing I want to do now is to introduce projective spaces. So this is must now. How many, let me ask you a question. How many of you have exposure to projective spaces? Depending on your answer, I will decide where to start. So your response is very much needed. So Tithi. Hello, yes, Tithi.
Yes, sir.
Do you have exposure to projective spaces?
No, sir.
Nothing at all?
Nothing, sir.
All right. Now what about Roshni? Hello, Roshni. Are you there?
Yes, sir, I am there.
And do you have exposure to projective spaces?
A little bit, sir. I have solved a few problems related to this piece.
All right. Then who else can I ask? Sonakshi is there? Sonakshi is not there today.
She is not there, sir.
Who?
Sonakshi is not there.
Is not there. All right. Anybody want to comment something which will enlighten me? Where will I start?
Sir, in recent lectures of complex analysis, we have seen that the automorphism group of upper half plane is isomorphic to PSL of R.
All right.
PSL, that is special linear projective space.
And what was the definition of PSL2 there?
Yeah, it was SL2 quotiented the identity matrix plus minus identity. Plus identity and then minus identity matrix. It was seen as the quotient fact.
All right. All right. Anyway, I need a projective spaces. So I will recall first projective spaces. And this is affine spaces. That is why I spent so much time earlier. So I will use, but not so much. I cannot afford to spend so much time. So I will do it more quicker way, and many statements I will not prove. I will summarize the things, and statements will ultimately get reduced to linear algebra, where we are assuming that you have a basic understanding of linear algebra. And so was the case in affine spaces. All right. So suppose I have a vector space V. V is a K vector space. And K is, I'm not assuming K is R or C, I'm assuming any field. Because we want to discuss the finite fields also. All right, now what do? I want to define PV. What is the projective space over V? Remember, I have also defined affine space over V. So this P I will denote by PV, and this PV will be extended from affine space. And the motivation why? How did we extend it? I will tell you the first roughly, and then we can make it more and more precise. See, in affine space, we know. So, for example, affine space over V, suppose V is R2. Then we have this vector space. This is the affine space. And when you say R2, the origin is chosen to us, given to us. And that affine space, affine linear map, that we have discussed so long in earlier exercises, earlier lectures, and so on. All right, now here, if I take two lines which are parallel, they don't meet anywhere. That is the definition of parallel lines or parallel affine subspaces in general. So it will be nice if they meet somewhere and a unique point, because we know if the lines are not parallel, they meet exactly at one point if they are different lines. And that is where I'm going to add somewhere at infinity horizon. When you look at the horizon and see the sky is touching the earth and so on, then they meet. And that means what? I'm attaching a line at infinity. And then that parallel lines meet at a point at infinity. Now, if you imagine a parallel line is attached at the infinity, now one might feel that one direction it will meet somewhere and the down direction it will meet somewhere. So you have to close it up something. In topology, such a thing will be known as one-point compactification. But that is done for real numbers, complex numbers, and so on. So for finite fields, such a description you cannot imagine, because the fields, the topology, what you will get is a discrete topology. All right, so with that in mind, and now another point I want to tell you, there is a projective geometry attached to the projective spaces. That is nowadays it's not studied in the universities, but earlier days it was studied very much. But now again, it is coming into study because of the various applications, especially from the mobile industry. So therefore, the main problem is to study linear algebra carefully. That is why if you go to subjects like artificial intelligence, data structures, the main requirement is a good understanding of linear algebra. So you see it here also. All right. So what is the projective space over V? So that is, I write first formally. So when you write formally, you can check easily, but maybe you may not be able to get a visual feeling or another remarks which are more important to understand them. But that usually you inherit from your teachers. So did I do. So everybody does that. All right. So this is one-dimensional subspaces. Kx. Kx is one-dimensional and x has to be non-zero. So x is varying in V and x is non-zero. So this is the set of all one-dimensional subspaces of V. So what are they? They are lines. We are calling them lines. Remember, dimension 1 objects in a vector space, they are called lines. Dimension 2 are called planes. Dimension 3 hyperplane is one-dimensional less. Right? So these are the lines passing through origin because they are subspaces. So the points in a projective space are lines which are passing through the origin. All right, this. I'm going to put more structure on this so that we will study that. So this is called the projective space. Space corresponding to V. Now, how does one think about it? So I have to relate with the V also. So obviously we have the map here. So look at the map. V minus 0 to PV. Namely any x goes to kx. And this kx I am going to denote by this x. This also matches with if you have used x is a subspace spanned by V, subspace spanned by x. All right. So this is the canonical projection. This is a subjective map. This is, I keep calling it a canonical projection. What are the fibers? See, this is a subjective map. So the map will be completely described if you know its image and the fibers. So the fibers, what happened? Fibers. You have, I know you have studied similar such language in the topology also. So this map I am going to denote by pi v. So what I'm asking is what is pi v inverse of this? This is the point in the image and I'm asking which x go to that x. So what is the answer? What is the answer? Can somebody say? Roshni, can you tell me what is the answer?
Yes, sir, it will be this space crossed with the other coordinates.
Your voice is splitting. I didn't understand.
I said that this x, the space kx, cross with the other spaces.
I have not understood. Anyway, I will write. So what the expected answer was, these are precisely the points on the line kx. Other than 0, of course. Non-zero points on the line. See, this x will determine a line, and therefore if I need that line I thought as a point here, and if I want to pull it out, they are the points, non-zero points. That is why this zero is omitted. So that is the answer. The fibers are the points on that line, non-zero points on the line. So when, suppose I take two vectors, x and y, in v minus 0, when is pi v x equal to pi v y? That is if and only if x and y are linearly,
they're on the same line.
X and y are linearly dependent.
Yeah.
Dependent over k. So that means y is of the form lambda times x, where lambda is a non-zero scalar. That is how we understand. All right. So the lines are also identified. If somebody may take the same line equation I saw in Nitin's lecture, he said this vector or that vector will determine the same line because they are linearly independent. And not only these are the unit vectors. If you take vectors of length 2, that doesn't matter, whichever direction. All right. So that is, more understanding will come. All right. So now in the coordinates, so this is what happened. I have not chosen a basis. When you choose a basis, then the coordinates will come in. So instead of writing a point, you will write x equal to AB. That is the vector. Similarly, if you take in a higher dimensional space, then you will write A1 to AN. And this is with the standard basis, or you can choose a basis and these are the coordinates with respect to that basis and so on. So that is your maturity with the basic linear algebra. All right, so I will just recall for simplicity. So suppose I take vector space finite dimensional and suppose it is n-dimensional vector space V. Then we know this is isomorphic to k power n as a vector space. So now if I want to explain this thing in the terms of the coordinates, I will choose a basis here E1 to n, standard basis, and that V or x, non-zero x, will correspond to a point here, and that point is usually denoted with the coordinates A1 to an. That means we have written this corresponding to x. That is, this is also written as A1 E1 plus AN EN. And these A1 to AN are coordinates with respect to the standard basis. That is how we use the standard coordinate system. So like this, for example, this picture is a standard coordinate system. R2, this is E1, this is E2. And then any other point, non-zero, we write in terms of the coordinates. All right. Now, therefore, what is the corresponding map? That's what I want to describe. So that coordinates are introduced usually for calculation purpose. And otherwise, you deal with the vectors. All right. So what is that? Therefore, I have to explain you what is k power n minus 0 to p k power n. And what is this map? A1 to AN. And that will go to, I will write it and explain you. This is what we have written. And remember, this is a non-zero point. That means one of them is non-zero. And what does this mean? This means a line determined by this vector. All right. All right. So now this is usually denoted by one less. That means this, I'm writing this notation is P n minus 1 over K. This is what is usually denoted by projective space. Why one dimension less? Because one of them is non-zero. So let's say I assume an is non-zero. In that case, this is same as a1 to an minus 1, comma 1. I can divide by that and I get the same line. Therefore, it is used this. So these are called the projective coordinates. These are projective coordinates. And these are affine coordinates. So usually what you study in your basic linear algebra courses are affine spaces with affine coordinate, because the calculation is easier in that case. But then you are missing the geometry. All right. So more than that, I will not say it now, because I want to go a little quickly. Now, similar to the affine spaces, we have to describe what are the projective maps. Projective maps and projective automorphisms. That's what I want to define. Like we have defined affine automorphisms or affine collineation. They are the same names, no? Affine collineations, affinities, and affine automorphisms we have studied for Kn or any vector space V we have studied. Similarly, similar concepts I have to define for the projective spaces. And you see, if you take a vector space of dimension n, this projective space will become one dimension less. That means what I am saying, I will write the formula. So that means, so I will write down the first one, the dimension of PV, dimension over K. That is same thing as dimension of V minus 1. Simple reason is, if you have just taken two-dimensional, then you only get a line. Therefore, dimension should be 1, and that is the reason. If you take a 0, V is a 0 space, 0 vector space. So what should be PV? PV should be empty space. When V is a one-dimensional, V just K, then it should be point only. So this is a point. Because there is only one line and you have identified with a point. All right, so, and if you have a plane, then we have identified all the lines, and then we have, so therefore it is dimension 1 less. More explanation will come if you study more. But now I want to go to projective automorphisms or projective isomorphisms. What should it mean? So suppose I have a linear. Remember, affine case, what did we do? In affine case, there was a linear part and there was just adding one point. That is what the philosophy was, because we have not fixed the origin. We were free to fix the origin, and that choice we have. So that is why it was better actually than fixing the origin, because once you fix origin, then imagine your hands are tied. So you have to do calculation with that origin only. Similarly, when you study matrices, if you study matrices and not the linear maps, your hands are tied, because whatever entries in the matrix that you cannot ignore. But if you are allowed to study linear maps corresponding to the matrices, then you can choose a basis and describe this linear map in terms of that basis, and that matrix may be better because you will choose your basis accordingly, right? So that is the philosophy. So working with coordinate free approach has advantage. All right, so given a linear map, F from V to W, where V, W are finite dimensional vector spaces. I'm going to define a map from PV to PW. PV to PW. And very natural map. See, if you use the coordinates, you will struggle. But if you are coordinate free, you will easily write it. All right. So what is the map? So you know what is the PV element. So this map, of course, will depend on this linear map. So it will be denoted by this. And what is the definition? So take a point here. The point is a line here. And we have decided how to denote them. Point is X here, where X is in V and X is non-zero. And question is, where do you map? Using the map, where do you map this? You need a point in PW, and this has to do something with this given linear map.
Fx, that is line generated.
So what do? Take f of x and take that. And now you need a fact that this is non-zero. So it's not arbitrary linear map. So let me just say that I take a bijective linear map. And you know, writing a bijective linear map is saying thing that this is an isomorphism of vector spaces. Isomorphism of vector spaces. Then if x is non-zero, then f of x is also non-zero, and that is the definition. So now again, I want to claim that this is an automorphism. This is an isomorphism again. This is also bijective. And to justify it is bijective, I have to write down the inverse. And what is the inverse? Any y should go where? Y non-zero, that should go to f inverse y. So that means the inverse of this map is precisely defined like this. Is that clear?
Yes, sir.
Yes, sir.
All right. So this evaluated at y is by definition is f inverse y. And this is for any y in W, y non-zero. So therefore, this is a projective isomorphism. This is precisely the projective isomorphism. So let me say that vector space isomorphisms will induce projective isomorphisms. And now I take V equal to W. Take V equal to W. And then I will talk about affine automorphisms or engine that is odd KV. These are automorphisms of the vector space. Of V. And we know it is a group. And these were the group which was canonically operating on V. Right? And that was connected to the affine space group, affine group. Similarly, now, if I have this, then I will have a group of projective isomorphisms from V to V, they are precisely the automorphisms of PV. So automorphisms of PV, you see, they correspond to the automorphisms. But now, because of this, of course, this group is connected to the group I am going to write here. So that is precisely called PGLV. Because this group is also, I have been sometime writing it GLV. So this is projective general linear group of V. So what are the elements? They are automorphisms of the projective space PV, and they are therefore coming from the elements of GLV. And so therefore we have this natural map GLV to PGLV, and this map is what? F here going to this bracket F. And obviously this map is surjective because of the definition. And the kernel is what we have written K cross, not K cross. Kernel is the center of GL, which is element. This instead of saying center, it is better to say it is K cross, because all these guys, if you see, all these guys are determined lines. So if you go mod that K cross, they give the same thing. That is the reason. So that is how we got that sequence which I wrote in the beginning today. See, this sequence. That explains this group. Where is it coming from? Algebraically, it is GLKV mod the center. And now the advantage is this group. So what do I want to exploit more now is the following fact. Is PGLV operates on projective space canonically. Why canonically? Because it is so, it's a automorphism groups operate on automorphisms of any object. Now, since you have been also, I've been hearing that you were sometimes talking in the categorical language. So automorphism of, for example, for a group G that operates on G by evaluation. Automorphism of V operates on V by evaluation. Automorphism of a ring operates on that ring by evaluation. The group of, for a topological space, automorphism group is precisely the group of homeomorphisms that operates on X canonically. Also, you can take any object that you are studying, whichever subject you are. If you are in complex, if you are in topology, algebra, also differentiable manifolds, and then you have to take the corresponding structure preserving maps, which are inverse bijective structure preserving map, and their inverses also bijective structure. Bijective is obvious, but structure preserving. Those groups are called isomorphism groups of those objects, and then those operates on that, and every subject you study this. The Galois group, when you have field extension, you have a group attached to that, and you say that Galois group operates on that, the field extension, and you study. What do you study exactly? You study the orbit stabilizers and so on, and from this you get information. So it depends how the automorphism, how big are the automorphism groups. The automorphisms groups are bigger, then you have more opportunities to draw more conclusions. If they are smaller, then you cannot draw much conclusions. So, for example, now since I raised this topic, I will make this opportunity to comment something. So, it's starting with the sets. This we are also doing it. Sets, monoids, groups, then rings, fields, so field extensions. Or topological spaces. And let me just take few objects. Now suppose I have a object here, set, typical set is a set with n elements, 1 to n. What is the automorphism group of this? Let me call this as IN. What is the automorphism group of this IN? Then monoids, M. What is the automorphism group of monoid? M. Groups, G. Automorphism group of G. Rings are automorphism group of ring R. So you write here rings so that you remember what structure you are taking. Here you are writing groups. Here you are writing monoids. Here you are writing sets. These are the categories you have. This is a category, 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 this is also category. This is also category. So field extension K, then automorphism group of the field K. Field extension L over K. Then you have the automorphism group of L over K as K algebras. That we are denoting Galois group. That is precisely called a Galois group. Topological spaces X. Then you write odd X means homeomorphisms. These are homeomorphisms. Now I will list some groups. So first of all, can somebody tell me what is odd IN as sets? Rahul.
Yes, sir.
What is odd IN as sets?
It is SN, sir.
SN, very good. This is the permutation group SN. You saw we spent so much time to understand SN and still not understood very well, but we have understood some extent what is order, how to find the orders of the element there, and so on and so on. All right. If I take G equal to, let us say, the group cyclic, G cyclic, then we know the automorphism group, no? Suppose G cyclic of prime order, then definitely we know. G cyclic of order P. Then what is the order of this group at least? Can somebody say?
P minus 1.
P minus 1 order. So you see, suppose I take ring to be Z. Can you tell me the automorphisms group of Z? Or Z?
Under trivial.
Trivial. Because remember, ring 1 goes to 1, therefore automorphism group of a ring Z is trivial. So such a thing is called rigid. Then there is no room to play. What is automorphism group of Q as a field? Or what is automorphism group of a finite field Z mod P? Or what is automorphism group of R as a field? Odd C. All these we know. Can somebody say what is odd Q? Odd Q as a field.
Q star, Q cross.
It's not true.
Or identity, sir.
Yes, very good. Automorphism group of R.
It is again
I saw
identity.
Nitin talking in
So
last
for all fields, isn't it just the identity?
automorphism group of a field Q. Ishan, what is the difficulty?
No, I'm not saying that. I'm saying these should be trivial, right?
Of which group you are talking about?
The field RC.
R is trivial, that you learned, no?
Yes, that's what I'm saying. So you were asking about what R, so I was saying that.
Odd Z mod P. Odd Z mod P. How many elements?
ZP star, right?
As a field,
So it is identity again.
No. Sorry, as a field. No. I'm sorry. I was thinking about it as a ring. Sorry. Of course, it's identity.
identity. Can you prove that?
Yes, one has to go to one.
Yes,
And
that is the
determines the
matter.
whole.
That is what the punchline.
Yeah.
Automorphism groups of C.
So it has cardinality more than 2.
It is in fact uncountably many. Automorphism group of a finite field extension. So if this extension is finite, then you know the Galois group is also finite and it is bounded by the degree of the extension. That is the first theorem one learns in the field theory. That is called Kroneker's theorem. All right. So when do you call the objects to be symmetric? When the automorphism group is maximum possible. When do you call that object to be rigid? When the automorphism group is trivial. For example, Z is a rigid ring. Q and Z mod P are the rigid fields. R also is the rigid field.
So
C is not a rigid field. And so on. This is just a language. And when do you say these are the symmetries? Some people call these elements of the automorphism groups as the symmetries. So symmetry is nothing but an automorphism. Yes.
Yeah, you said that rigid is the trivial thing, but you said it is symmetric when the automorphism group is maximum possible.
Let me complete my sentence. Whenever you have a possibility to see what is the upper bound for the order, then you say if the upper bound is attained, those objects are symmetric. All right.
Okay, thank you.
Now you see the ring R is real numbers, that ring R is not symmetric. Ring Z is not symmetric. It is the other extent. It's a rigid one.
Can I ask a question on what you just said about that upper bound thing?
Yes.
You said that if there's an upper bound and that upper bound is attained.
Yes.
But there can be many upper bounds, right? So are you talking about a best?
There is only one upper bound. Whenever you have upper bound possibility, whenever automorphism group of any object is finite, that cardinality is determined.
No, but even if I say that if I take IN, okay?
Yes.
And I say an upper bound, of course, one upper bound is n factorial. But if I take
that is the only one.
So why is n factorial plus 1 not
because once you take IN, isn't automorphism group is determined?
Yes, the automorphism.
Therefore, the order is determined. Therefore, the upper bound, it's 1. It's n factorial.
Okay, so my confusion is you're saying.
For example, let me give you an example. For a group G, see what are the maximum possible automorphism cardinality can be for a group. Finite group. I am only talking finite group.
One possible upper bound.
Suppose G is order n, then what are the possibilities for the number of automorphisms?
I know
it's bounded, no?
Yes, it is bounded.
Yes.
It is in factorial.
So if that is attained, then you call that G to be symmetric. Because the number of symmetries of the group G is maximum possible. See, it is not easy to see that what is the bound, sharp bound. For example, I don't know the following, how one can prove it. When do you call a topological space to be rigid? That means, given a topological space, how can I decide there is only one homeomorphism from X to X? That I don't know how to decide. In that case, I will call that topological space to be rigid. All right. So that is the one.
Okay, thank you. I don't want to take up more time, so I will ask you at the end. There's still some.
Fine. I am only saying symmetry. I just wanted to say what is a symmetry in general. Symmetry in general is an element of what? So now whatever object you talk in a category C, whatever object A you talk in a category C, then odd A in the category C. That makes sense, right? And this is a group. And the elements of this group are called symmetries of A. So now you can take that A, C to be the category of sets or monoids or groups or rings or field extensions or topological spaces, or you can think of any category and their objects and ask how many automorphisms are there. And the more the number of automorphisms you have, the more the symmetries you have, and therefore the object will be more and more symmetric. So, for example, if you take category the triangles in a plane and distance preserving maps, and then you take that, then arbitrary triangle won't have any symmetry at all. But if it is isosceles, then you will have some symmetries. More symmetry will come only when the triangle is equilateral. And you see, that is beautiful. That is symmetric. Similarly, you can do it quadrilaterals and so on and so on. So this is a big field. So if you want to have more fun, just go and see what is beautiful in Oxford Dictionary. Or what is symmetry in Oxford Dictionary. These words are coming from the dictionary only. The mathematicians are not taking arbitrary words. All right, so enough that our time is going up. So in fact, I want to describe now PGLV operates on V canonically, that we know now. Because how does it operate? I will stop with this operation. The PGLV is a group cross PV to PV. I want a map, operation map I'm doing, which should satisfy those two obvious properties. So PGLV, what are the elements? They are coming from linear maps and we are denoting like this. And these are, F is an automorphism of V. Or V. This, comma, any element of PV, you are writing like this, X, where X is a non-zero element in a vector space. And this pair, where does it go? Obvious. It is going to F this evaluate at this X. Make sense? That is what I defined. That is what I have defined. Fx over. So that is it. This is precisely Fx. So this is the operation map. And next time I want to digress you from a little bit about how is it connected to the Mobius transformations. And then the next thing I will analyze is if this operation transitive or not, and more than transitive, is a doubly transitive or triply transitive. And this is what will help me to determine the structure of PSLV. And I want to ultimately decide whether PSLV group is simple or not. And for a finite field, we will prove that it is simple. And that was the aim of Jordan in 1870, to describe some or to get some precise or concrete examples of simple groups which are different from the alternating group family. So that is what we will continue next time. I will now close the lecture and send the PDF file to the Purnashri and Makaran. They will